And welcome, everyone. Thanks so much for joining us for the Battery Insiders podcast. I'm extremely delighted today, as Simon Engelke, the founder and chair of Battery Associates, as the host of today's episode, to talk to Lord Turner, who's the chair of the Energy Transitions Commission, which is a global coalition of companies to identify technical and economical challenges to get to net zero in all the sectors. And I was very fortunate to see you speak in the context of one of the large OEMs out there, and really sharing, I think, a lot of your good insights and also a lot of enthusiasm of what is even possible in this industry. And I'm really delighted to speak with you today. Thanks for joining us.
Thank you.
Brilliant. So let's get right into it. I think I just touched on, with your coalition, you look at technological challenges. So let's talk a bit about technology. And of course, here as part of the Battery Insiders podcast, of course, we're also quite interested in the battery side. And to maybe start on the technological topic, talking about cost and scalability. And of course, we have seen that the battery price we have plummeted. It's really exciting, especially on the stationary side as well, but also, lithium iron phosphate, but also topics such as sodium ion, which could still drive it down even further. So looking at all of these developments and the rapid developments and the possibilities of scale up, right, to terawatt hour levels of storage, what do you see as some of the bottlenecks to really make this happen? Supply chains, for example, is a topic people talk about, manufacturing, anything else which can stop this massive transition we're seeing?
Well, I basically think we are on an unstoppable transition to a dramatically increased role of batteries, and in particular, probably lithium ion and maybe sodium ion batteries in our energy systems. Since I began to be very involved in issues to do with the energy transition about 15 or 16 years ago, 17 years ago now, 2008, when I became the first chair of the UK's Climate Change Committee, one of the most dramatic and, at that stage, unexpected changes has been an extraordinary fall in the cost of lithium-ion batteries. I mean, essentially, they are down 90% in price, or even more than they were in, say, 2008, 2009, when I first started working in these areas. And this has transformed the prospects for electrifying the global economy. It transforms the prospects for electrifying road transport in particular, but it has also transformed the prospects for storing electricity within grid systems, which enables us to deploy renewables far faster than possible. Far faster than we previously thought was possible. It really is a major change and has changed my point of view over the last 10 to 15 years as what is possible. Now, people then say, well, there are constraints. I have to say, I don't think there are major constraints, or every time we think there's a constraint, it turns out that it isn't an important one. I remember 5 years ago when the main technology we were using, the main chemistry mix we were using in a lithium-ion batteries was NMC, nickel, manganese, and cobalt on the cathode. And people were worried about, well, how are we going to get enough cobalt? Most cobalt is coming from Democratic Republic of Congo with all sorts of environmental and child labor and political corruption issues. What about the price of nickel? And then, to an extent which I did not see coming about 5 or 6 years ago, a wave of innovation gave us the lithium ferrous phosphate battery, which requires no nickel and no cobalt. And as a result, the cost of cobalt and the cost of nickel, having gone up by about 3 or 4 times between about 2019 and 2022, are now down to back with the way they were before. Because it turns out, although nickel and cobalt can enable us to have very high performance batteries, we don't need them in all batteries. And over 50% of all the batteries now being produced in the world are LFP batteries with no nickel and cobalt. A complete change in just 5 years. As for lithium, there is lots and lots of lithium in the world. And again, we've seen a rise in the lithium price between 2020 to 2022 of about 4 times. And we've seen it completely reverse. And that's despite the fact that there's an extraordinary boom going on in battery energy storage systems using lithium-ion batteries. And despite the fact that actually electric vehicle sales across the world are progressing faster than was predicted 5 years ago. Now, of course, there may be mineral supply pinch points that develop in future, and there are very important local environmental impacts about mineral development. For instance, I'm very worried about some of the local environmental impacts of the big nickel production developments which have occurred in Indonesia. But overall, I think we should be confident that all the mineral supply issues will be solved by finding new resources, by new and less environmentally harmful processing technologies which are being developed, and then later by the recycling of battery material. Now, of course, that at the moment is relatively small, simply because we haven't yet got to the end of a big generation of EVs. But within 10 years' time, I think a significant proportion of all the lithium and the nickel and the cobalt, to the extent that we're still using lithium and cobalt, going into electric vehicle and stationary batteries, will be coming from the recycling of the batteries at end of life. So my overall belief is this is unstoppable. And when we at the Energy Transition Commission have looked at the environmental impact on this of the world, of course there's an environmental impact. Human beings can't have a high level of prosperity without some environmental impact, but it is an order of magnitude less, or 2 or 3 orders of magnitude less than the environmental impact of the fossil fuel system that we're replacing. So I really am an optimist of this. It's one of in a very tricky and worrying world, this is a technology which can transform humanity's prospects for the better.
Really appreciate it. You said it, closing the loop, circularity, definitely topics you can touch on more later as well. Maybe talk about one aspect you touched already on, a lot of the benefits. Another topic, of course, is the topic of long duration storage, right? Mm-hmm. If you think about lithium ion, you just mentioned, we often think about 1 hour, 2 hour, 4 hours, maybe a bit more. But then, of course, we also have other topics, we have seasonal times, right? We also have loads of the, longer time where, it's darker, maybe in winter. Maybe, there's time when the wind is not blowing as much. So things like that. So maybe what are some of the other technologies we need for that? Is it then redox flow? Is it hydrogen? Maybe could you share a bit more on the topic of long duration storage, what you see in that regards?
Well, you're absolutely right. It's very important to understand all the durations across which we will have to shift supply via storage to balance supply and demand in a variable system. And in fact, the Energy Transition Commission will be producing a major report in July, which sets out that picture. Interestingly, it's very different in different regions of the world. If you look at the challenge which India or Indonesia or Africa will have, it will be almost entirely, very primarily, a diurnal challenge, right? It will be, you have a whole load of solar PV by day. How do you keep the air conditioner running when the sun goes down? Much less in those countries, seasonal variation. When you come to Northwest Europe, by far our biggest balancing challenge is what to do in a February winter when we get an anticyclone in the North Sea, where the wind supply goes down, not for an individual hour or day, but goes down for maybe even 2 or 3 weeks. 2 or 3 weeks, which might happen once or twice in a winter, but you don't know when exactly they're going to happen. And if that's a very cold anticyclone, it might correspond with precisely the point where there is high electricity demand, if, as we should, we have electrified heating, getting rid of the gas boilers and replacing them with heat pumps. So we have these different balancing challenge. We have short-term, essentially diurnal, 2 hours, 4 hours, say 8 hours, but not more than that. We have weekly and a couple of weeks, and then we have these long seasonal ones. And we have to deploy a set of technologies to address each of these different duration challenges. Now, interestingly, when you look at batteries, technically, batteries could solve any of these, right? There is no limit to how slow you can charge and discharge a battery. A battery has a maximum C rate, a rate at which you can charge and discharge it, but that's a maximum. You could take a battery and slowly fill it up over, a week and then slowly run it down in a week. The reason why we don't think we'll do that is not technical limitations, it's economics. Batteries have in the past cost so much per kilowatt hour storable that they're only economic if we're going to be cycling them many, many times per year. If we're going to be cycling with them at least, say, 365 times a year, charging them up in the day and discharging them at night. An interesting issue is how low can battery costs go, and does that challenge that assumption? Right? If I could give you batteries in 2010 cost in today's money $1,300 or $1,400 per kilowatt hour. Now at the pack level, they're going below $100 per kilowatt hour. If I could give you a battery which costs $10 a kilowatt hour, you might use it even for that very long duration storage. It's all an economic issue, not a technical issue. But at least for now, our assumption is that the batteries will do the 2 hours, the 4 hours, the 8 hours, the 8 or 12 hours, which is enough to solve all of the diurnal challenges. And that's really important because it means that in, say, the sun belt of the world, where there is a lot of sun and not much seasonal variation in energy demand, solar plus batteries is going to become an almost complete solution. Come again to the Northwest Europe or other high latitudes, we're going to need a range of technologies. Those will be batteries at the shorter duration. And then there's technologies like compressed air, maybe liquid air, maybe vanadium redox flow batteries at a slightly longer level, pumped hydro, very a powerful technology wherever we have the physical situation. Of course, best when you've got some mountains, some elevation, because it's all based on gravity. Heat storage, a very interesting one, just heating up bricks or stones with electrical input when we've got surplus electricity, and then releasing that heat either to be used as heat or to drive turbines when we need it. Now, of course, one of the biggest challenges is those really long cycles that I referred to earlier. How to take, say, surplus wind that we would tend to have in October and November with autumn winds, and to store up enough energy that we can deal with this, as is in the German word, the Dunkelflaute, the doldrum of the February or so anticyclone. Here, I think hydrogen is going to be the dominant technology, making hydrogen from electrolysis when we have surplus wind and solar and storing it in salt caverns. The analysis, for instance, for the UK suggests that we have lots and lots of storage in salt caverns, and the cost of doing that is relatively low. So the capital cost per kilowatt hour storable is so low that it doesn't matter that you're only cycling it once or twice or 3 times a year. But there are significant conversion losses, of course, because what you will do is you'll make the hydrogen and then almost certainly get it back to electricity by burning it in a gas turbine. And the combination of the loss in the electricity, the electrolysis process, and in the combustion process will probably be 50% or so. So by definition, the electricity that comes out at the end is going to be twice as expensive as the electricity that you put in. But there are these full range of technologies available, and we are confident that they can solve the problem, though with this interesting wrinkle that I think the challenges of balancing supply and demand we are going to find much easier and much cheaper in the sun belt of the world than in the northern latitude wind belt.
Brilliant. So what I hear from that is in some region it can be a full solution with best with battery storage. In some others we need to complement with other technologies.
Absolutely.
Right?
Absolutely. Yeah.
Fantastic. So another application, right, of batteries is electric vehicles.
Yep.
And electric vehicles, of course, and that's also the context where we were first connected. But then, of course, also the topic how you can maybe use even EVs, right, as a stability to complement vehicle to grid for the grid as well, and kind of enable, and demand response and smart charging and things like that. As you mentioned, we have more EVs coming online maybe than people anticipated 5 years ago, but there's still a range of challenges, right, from infrastructure and others for EVs. Maybe you could share a bit more your perspective on what we have to do now to really scale up further, right, to these millions of EVs which we require in the system, and maybe what are some of the challenges to overcome in that regards.
Well, of course, it's interesting. We sometimes talk about these challenges as if, oh, we got to work out what they are. But let's be clear, there are two major countries in the world, two countries, one very big, one relatively small, which have solved these problems. I mean, Norway now, 95% of all new vehicle sales are electric vehicle, and primarily straight battery electric vehicle, not plug-in hybrid. And when in the UK people say to me, "Oh, Adair, these battery electric vehicles, they won't work in cold climates because the batteries don't work as well in cold climates, and they won't work in countries with long driving distances," I say to them, "Well, have you ever been in Norway? And can you give me an explanation of why it's working in Norway?" The answer is, if you invest enough in charging infrastructure, then the EVs will be the solution for the whole of passenger cars. And I think we've got to the stage, took a long time in relation to Japan in particular, where we've realized that the idea of the hydrogen passenger car is a complete delusion. Battery electric vehicles are fundamentally advantaged. They are much more efficient. They're silent. They don't produce local pollution in cities. They have far higher acceleration for people who enjoy that sort of thing than old-fashioned, noisy, inefficient internal combustion engines. These are going to win. And in China, of course, we're just at the stage where a big country, rather than Norway, a little country, where they're going above 50% of new passenger car sales. And I suspect that by 2030 in China, there'll be 90% of new passenger car sales. So I think it's important to realize this is a revolution which is absolutely unstoppable. And with the fall in battery prices, we are probably only 2 or 3 years away from getting to the point where the battery electric vehicle is cheaper than the internal combustion engine vehicle for the same sort of size and comfort level. And again, that point has already been reached in China. And the other dimension of a innovation and battery technology advance is not just that the costs are coming down, but the energy density is going up. Energy density is measured both gravimetrically as watt hours per kilogram, volumetrically as watt hours per litre. But both of those, volumetric a bit faster than gravimetric, are going up at maybe 6 to 8% per annum, doubling every 10 years or so. And that's why we are now seeing coming onto the market EVs with ranges of 350, even 400 miles. Let me do that in kilometers. 500 kilometers, 600 kilometers, which will meet almost all people's needs for range. So this is unstoppable. What is interesting about that, and it's the other question you asked, is, well, what is the implication of that for the power system? Because let's run some interesting little numbers here. Suppose by 2050, all the car fleet, which will then exist, is electric. Let's say that's 1.5 billion cars, all of them electric. And suppose they all have, on average, a 60 kilowatt hour battery. That means that we will have, sitting out there on our streets, 90 terawatt hours of battery capacity sitting around. And one of the features of passenger cars is that when we're talking about the individually owned passenger car, not the car fleet, the taxi, but the individually owned passenger car, they're typically only used about 5% of all the hours, or sometimes less. The other time they just sit in the garage, sit on the street. 90 terawatt hours of storage capacity. By then, we might be consuming across the world, say, 70,000 terawatt hours of electricity per annum, 2.5 times up from today's level. 70,000 terawatt hours per annum is about 190 terawatt hours per day. So we're going to end up with a system that has demand per day of 120 terawatt hours, And we've got, sitting in the street unused, 90 terawatt hours of battery capacity. So the challenge is clearly, how do we use that? Because it is so much that if we worked out how to use it, we could solve all the short-term duration balancing needs, not with having to put even more batteries into the stationary storage element, but by just using the batteries which are in the EVs. Now, at one level, this is very exciting technology. At another level, I first heard this idea 10 or 15 years ago, and we're not really seeing yet a lot of all this sophisticated vehicle-to-grid type a sophistication that people have talked about, signing up to a tariff from your electricity provider and agreeing that as long as you let them software control your battery, they can put electricity in and take it out. The first step is to simply strongly encourage people to, at very least, charge that growing fleet at a sensible time of day. And of course, this is also true to a degree, but somewhat less a degree in heating buildings. This issue of how do we get people to use electricity when it is surplus to requirements, say in the northern latitude, in the middle of the night when we've still got wind, or in sunny parts of the world, in the middle of the day when there's surplus solar electricity. And here, time of day pricing of electricity is absolutely crucial. I was recently talking with one of our members, Ausgrid, major a distribution company in Australia, and talking about the fact that there are parts of Australia now where electricity is free from 11 a.m. to 3 p.m. because there is so much rooftop solar that the grids don't want to pay that rooftop solar to produce because it's excess to requirements. And indeed, the system itself is excess to requirements. So what they're trying to do there is saying, educate people between 11 and 3, electricity is being thrown away. So please charge your car in that period of the day. So there is a huge potential to use this enormous a passenger car fleet battery capacity, first of all, to shift electricity demand to times of day where we've got surplus electricity. And I'm sure that will occur to a very significant extent over time. I think we will achieve that revolution of people being sensible about when to charge their car. Whether or not we then progress to the sophisticated level of the battery also putting electricity back into the grid on a complicated software controlled process, I don't know. But if we achieve the first, we will dramatically reduce the costs of achieving the balance of supply and demand within systems with high levels of renewables.
Right. And sharing that, and I think expanding a bit on that, right? I think I want to go maybe to the topic of policy and regulation. And I know also, again, for the vehicle to grid, for example, there's two topics, right? With the inverters, maybe a bit more technical topic. And then maybe with the regulation, having the right energy markets. Maybe we can go a bit more into that now. I mean, a big topic, of course, also in Europe, also people talk about, but also in other regions, right? The topic of permitting, right? For these getting these systems, especially BESS systems as well. There's a lot of different kind of regulations, or there's a lot of question marks about how to really set this up in effective ways, get this rollout, right, of these systems out there. I've heard of very creative ways with like having, these containers on movable vehicles, so you can move it around, which is easier from a permitting stance in certain regions. So all kinds of kind of complicated topics there for also getting these, BESS installations, but then of course also connect to wind and solar farms. So maybe if you could share a bit about like what you have seen maybe out there from a regulatory perspective, kind of what has worked well, maybe about some challenges, and to get these systems online as quick as we can, because that's something I think we're all very passionate about.
Well, if I can begin by, you mentioned these containerized solutions. This is a really important technological innovation, which has really occurred in the last 3 or 4 years, where the battery producers are putting the battery packs have cells within them and then various packaging around them, and they're putting them in shipping containers, literally TEUs, as they call, 20-foot equivalent unit, the actual, shipping containers, these extraordinary things like a Lego brick, which just move in this highly standardized fashion. So they're putting them in then with different degrees of integration of things like inverters, so that you can buy now what's called a DC block without an inverter, or you can buy an AC block with an inverter, a DC to AC converter within the system. And these are creating systems which then, to a significant extent, are making battery energy storage closer and closer to what you might call plug and play. You get your container and you just plug it into the system. And this has driven down the costs, because within any battery system, it's quite interesting. Until about 4 years ago, the cost of stationary battery storage was much higher per kilowatt hour than the cost of EV battery storage. And at one level, that was a bit odd, because with EVs, we've got this challenge of getting them into the smallest space possible. But because that market had developed more, because it was more standardized, because we had large automotive OEMs giving large standardized orders to producers, that had developed faster. What we've now seen in the battery energy storage market is this containerized solution, much bigger scale, and all what's called the BMS, the battery management system costs, which are on in addition to the packs, which are in themselves addition to the cells, the battery management systems coming down in cost. Now, that doesn't immediately get round the other problem that you mentioned, which is permitting, because these things do take up space. You've got to put them in a field. People may not like them, being that field, taking over, whatever that was before. Hopefully, as much as possible, we put it on brownfield land, but sometimes it will be greenfield land. So it generates the same opposition and concerns that any form of development has, whether housing development or onshore wind development or pylon development. I think over time, we will find this less challenges in terms of local opposition than, for instance, things like pylon development across the line, because, these things can be made, relatively invisible. They don't need to be all that high. We can use lots of brownfield land. We can go down a bit. We can, cut out space to take them down below the level of the visual sight, etc. But we are building a new electricity system, which requires new forms of development. And of course, every time you put in a large battery storage system, you are going to need some sort of grid connection. And that's going to create wires above or below the ground, and there may be resistance to that. So we've got to try to speed these permitting processes. We've got to try to speed the development of grids, though the really big grid needs will be generated by the fact that the offshore wind is in a different location than the coal was. We should maybe think about innovative ways of making sure we reuse assets that we have at the moment. For instance, every old coal plant has massive, great big grid connections with it. So when you close a coal plant, which is already a brownfield site, why not put a massive, great battery installation there, because you're using the existing asset rather than having to build new assets. The other thing to say is that the more that we can put in decentralized battery capacity into people's homes, into commercial and industrial sites, the more that we achieve our balancing of supply and demand right down at the local level, and then we don't need to do as much extension of the grid. We don't need to build as much new transmission or distribution grid, because we're balancing at local level rather than balancing across the whole grid level. So there's a set of intelligent policies to support decentralized storage, including in-home storage, as much as possible, solar plus batteries together, for instance. There is trying to develop as much as possible less visually, less space absorbing developments, using as much brownfield site as possible, using existing grid connections as much as possible. And I think we just need, very conscious policies to do that. I mean, the good news, of course, is that the one thing that battery installations don't have, they take up space. People don't like the visual impact of them, but they're not producing any effluent. They're not polluting. They're not producing noise. Compared with a lot of our existing energy system, they are less intrusive.
Brilliant. No, that makes a lot of sense. And then maybe I was talking a bit about going in the direction of markets, right?
Mm-hmm. Yeah.
Some of the incentives, maybe if you can share. I mean, you mentioned already individual, right? It would be good to have storage at home, but then of course also, larger installations. Do you think right now, there's enough kind of incentives out there to kind of support that?
Well, here's an interesting thing on the development of battery energy storage. I think, and all the long duration ones, which we talked about earlier, the challenge is just beginning. And it's quite interesting and important to realize how much progress we have made with decarbonizing electricity systems without doing a whole load of storage. So the UK in 2010, our electricity had a carbon intensity of 500 grams per kilowatt hour. In 2024, it was 125 grams per kilowatt hour, a 75% reduction in the carbon intensity of electricity. That's partly because we closed down our coal plants and used gas as our fossil fuel fleet. But it's also because we have grown renewables to, I think now, in excess of about 30, but pushing on towards 40%, wind and solar as our source of electricity. And so far, all that we've really done is switch the gas fleet to flexible operation. So when the wind blows, we shut down gas plants, and when the wind doesn't blow, we ramp up the gas plants. And so far, we've had very little battery investment and almost no long duration investment. And this is a very important message for countries like India and China. You can go a long way towards decarbonization if you can make your fossil fuel fleet more flexible. And although coal is inherently less flexible than gas, there's a whole load of new technologies that can make it flexible. So this is why, so far, although we talk about all these storage technologies, there hasn't been huge deployment, but we are now at the stage where we have to. So the UK is committed to get to zero carbon or close to zero carbon electricity by the early 2030s. We won't be able simply to do that by this trick of running the gas fleet in inverse to the solar and wind. We'll have to have bits where there's no solar and wind, but we're not running the gas fleet, we're doing something else. We're now at the stage where we're going to have to develop the batteries, the compressed air, the pumped hydro, the hydrogen. And we need markets that support that. It's interesting the different market structures that can support it, and I don't think one can be prescriptive. One of the things that you can do is you can do quantitative mandates. You can say, whenever you develop wind and solar, you have to put in a certain amount of battery or other storage capacity. You can do what the Indian government has done, very interesting a development, which is what's called the round-the-clock renewables contract, where in the major auctions for new renewable capacity and generation in India, typically the provider has to commit to delivering electricity 80% of hours per year. And indeed, they're now moving to an environment where it's not just 80% of all the hours at the developer's option. The system generator can say, and if I tell you 24 hours in advance, a particular half-hour period I need electricity, that needs to be one of your, 6,000 hours per year. And that then pushes to the developers the challenge of saying, okay, what is the combination of wind and solar and batteries which will enable me to meet that contract in almost all states of the world relying on very, very expensive wholesale electricity in the market if I get it wrong and I can't quite meet it in all states of the world. So that's another very interesting contract structure, and one which is revealing that these combinations of wind, solar and batteries are now cheaper than coal power in new coal power in India to provide electricity throughout the year. Really interesting test. Another structure you can have is, of course, capacity markets, where the grid operator pays people to exist as a capacity, and then they operate in the energy market off their marginal cost, which of course is very low. The crucial thing, if you go that way, is you must have neutrality of treatment between a capacity market that pays a gas turbine to exist and a capacity market that pays a battery to exist, or a capacity market which is a contract with a demand-side flexibility provider. And I think we've had a problem in the past that some capacity markets have developed in a non-neutral fashion. They've had a favoritism to basically say, I know I need my gas turbines to continue to exist, even if they only run 1,000 hours a year, therefore I'm going to pay them to do it. So look, I don't think we can be prescriptive about this, and I think what we've got experimentation going on, but what we undoubtedly need is system operators throughout the world thinking about the combination of this suite of techniques which will enable us to develop all the technologies and the business systems, the combinations of technologies which will enable us to run systems with very high levels of variable renewables. And we foresee systems where, yes, they'll have hydro wherever you've got hydro. Hydro is a beautiful resource, particularly dammed hydro, wherever you've got it. It's cheap and it's flexible. Yes, they will have nuclear. Again, if you've got existing nuclear, keep it forever if you can, because the zero marginal cost is low. But we see a world in which variable renewables, wind and solar, will probably go to over 70% of supply in almost all countries of the world. And we will need system operators which think very carefully about the combination of market design and contract structures which enables us to do that in a cost-effective fashion.
Well, and you just mentioned cost, right? And of course, another topic is the investment required, right, to get all these systems into place. We know that's a massive investment only on the battery side, right? BESS, what's kind of required there. But there's a lot of appetite as well in the markets. But yeah, maybe if you could share a bit more about, what could make it, is it attractive already now this year for the financial markets? Who's going to put the money in? Is it more individuals? Is it more companies? Is it more investors? Is it more governments? Who's really getting us most of the capacity?
I think it's going to be, in most countries, mainly private investors and private companies, private developers. It's very interesting. In the EV market, we don't even talk about really that challenge, because we just assume that there's some OEMs, big automotive companies that invest to build EV factories, and they do contracts with big battery companies. Now, if you want battery factories to be in Europe, not China, then you get governments stepping in and providing subsidies. But the core activity is done by private enterprise, and on the whole, it works well. And I think, broadly speaking, for most of these power sector developments, we are going to have private developers of wind farms, private developers of demand-side flexibility offers. One thinks of a company like Octopus in the UK, absolute leader in demand-side flexibility packages. And I think we'll see that in the battery space as well. And there is, for instance, intriguingly, huge investment now going into stationary energy storage in the US, despite the fact that they now have a president who, doesn't believe in this energy transition and wants to drill, baby, drill, and, absolutely enormous expansion going on. I don't think we should exclude a role for instance, infrastructure banks. And I think it should be focused on those things which are going to be most complex and first of a kind, and where you get complicated combinations of things that have to happen. So, for instance, as I say, I think battery storage will tend, provided we can deal with the planning and permitting, to be a relatively straightforward plug-and-play system. You get your battery container situations, you build as many of those you need together, you connect the grids. You don't, provided you can get the land and the grid connection, you can develop a business system for that quite fast. I think where we have to do, salt cavern developments, hydrogen pipelines, working out whether that's going to be retrofitting existing gas pipelines or is it new gas pipelines. I think we may have to have a role there for, say, national infrastructure banks, which take the first risk, which make it happen. Just as we are seeing, for instance, in the development of carbon capture and storage networks, where you're trying to build together multiple different players, cement plants here, somebody who has an old gas field there, somebody who owns a pipeline which is almost good but needs to be retrofitted. You sometimes need the role of the state, or more likely the infrastructure bank, to just sort of help lubricate those early complicated combinations of actions. But I think provided you have power market design right, provided you've got that suite of appropriate contracts, which I referred to earlier, I think most of the investment will come from the private sector, from private investors, long-term infrastructure in funds, pension funds, insurance companies, the sort of people who do long-term investments, and the private developers who put that together into profitable packages.
Brilliant. I think we have also, as battery associates, we have seen definitely quite a bit of demand on this side. So I think I very much agree with you on that. I think there's a lot of interest in these markets and from these kind of investors on this sector. Kind of the two last topics I want to touch on. Like the first one will be, you already touched on a few regions around the world, right? And kind of some of them, how they're maybe more ahead than others, and some maybe have some more challenging times. But maybe if you could help me a bit on, for the audience as well, kind of understand a bit like, where's Europe standing right now, but maybe also where are other regions standing on the storage type, on the energy transition topic, just to understand maybe also compared to China, North America, just kind of give a bit of understanding how we're standing in that regards.
Well, Europe, in some ways, is among the most advanced continents in a transition. I mean, of course, a country like Brazil has some of the cleanest electricity in the world because it's always had clean electricity, because it's always been hydro. So, but if you talk about countries that started with very big fossil fuel electricity systems and are trying to come out of them, Europe is one of the most advanced, and we have countries like Germany, Ireland, Spain, Denmark, Portugal already going over 40% of their electricity becoming from variable renewables. And that is increasing very significantly. And it's quite heartening that after the Russia invasion of Ukraine and the shock that gave us to gas supply, we did accelerate moves towards renewable deployment with the Repower EU program. And I think, and with action to free up planning and permitting systems, and investment is continuing. There's been a bit of a setback on the offshore wind industry, but I think we're going to see that bouncing forward again. The level of solar deployment in places like Germany and Spain and is quite extraordinary. That's been an explosion of the last few years. And then on EVs, on the electrification side, it's beginning to ramp up. I mean, there's been a lot of talk about, it's going slower than we thought. Well, yeah, but just remember, February, the figures are in for Germany, 30% of the new vehicles are EVs, and I think we're going to see an acceleration there. So Europe is making progress. I think it's making slower progress on things to do with its heavy industry transformation. In residential heat, a lot of progress, too slow in the UK. But on the whole, the UK has said it wants a zero carbon power system by 2030, let's say early 2030s. Europe has said by 2035. I think we're going to get pretty close to there. I increasingly think the big challenge for Europe being zero carbon in 2050 is what are we going to do about agriculture? What are we going to do about aviation? But I think by 2050 we'll have a primarily electrified road transport passenger fleet will have a primarily zero carbon. It doesn't need to be precisely zero carbon, but say 10 or 20 grams per kilowatt hour electricity. We're on target to do that. China is interesting because, of course, China emissions have probably just peaked. It may be that we'll find out that calendar year 2024 may be the peak, or calendar year 2025, is deploying renewables at an absolutely stunning rate. But what has been occurring so far is that electricity demand has been going up to match that. What we've been seeing is China installing enough wind and solar every year to produce about 300 terawatt hours of electricity, but electricity demand has gone up by about 300 terawatt hours. So that although the new renewables have been meeting all the increase in demand, the amount of demand which is met by the coal fleet hasn't gone down. I think we're probably at the turning point. It's obviously hugely important for Europe that once they go beyond that turning point, they come down as rapidly as possible. The early stages of that will be moving the coal fleet, beginning to occur already, onto a flexible process so that the coal capacity still exists, but the utilization rate goes down as it begins to flex in inverse pattern to the wind and solar. That's where China is, and of course China is ahead on electrification of road transport, way ahead, both in production and in demand. India is somewhat similar to China in that their electricity demand is going up very rapidly, actually going up slightly faster than the new renewable supply. So they really need to ramp up the pace of renewable deployment, but it has accelerated very significantly in the last couple of years.
Brilliant. Thank you for sharing that. And then as a final question, just in interest of time, maybe looking a bit into the future, right? Kind of what we can expect, what we can see. We can, I think, definitely tell you quite optimistic, I think, on some of these topics, which is, of course, really good to hear and to see. But maybe on these two topics we also touched on today, right? Or the three one, maybe more on the technology side. Maybe what are you kind of expecting what could come, to help on this regards, maybe also long duration or different chemistry like sodium ion. And then also the topic, from economical and policy standpoints, anything you kind of expect maybe to come over the next, let's say, 5 or 10 or so years.
Well, look, I think on emerging technologies, battery technology is going to progress and progress and progress. And we may see an acceleration of it. One must always be wary of saying that AI is going to accelerate, but this is one of these areas where artificial intelligence may accelerate our ability to explore all the different possible combinations of elements on the anode, the cathode, all the different ways that the battery chemistry works. It's similar to the fact we've seen this amazing breakthrough on AI in understanding protein folds in the organic chemistry area. I think in the inorganic chemistry area, just understanding every way that we can play around with the elemental table, the periodic table. I suspect it will accelerate, but it was going pretty fast even before that. I mean, there are two key dimensions of battery technology development. One is the cost and the other is the performance. On the cost, sodium ion, promises to enable us to produce just cheaper batteries per kilowatt hour storable. And the cheaper the batteries, the longer the duration which batteries can address. I mentioned earlier, if somebody can give me a battery at $10 a kilowatt hour at the pack level, then I think we're seriously into using batteries over, multi-day, 50-hour, 100-day cycles, or even longer, not just saying that they stick at the short duration level. So sodium at the moment, early stages, and of course, therefore, it's more expensive than lithium ion. But we know that if it becomes big manufacturing capacity, it will be lower cost than lithium ion, just because sodium is available in essentially limitless and very cheap quantities compared with lithium. I think what's interesting is, will sodium have an opportunity soon, or has lithium ended up so cheap that at least it's slowed down sodium? So people tell me sodium ion, pencil in that with mass scale, I might get it at the cell level to, $20, $25 per kilowatt hour. And they were saying that 3 years ago when the battery cell, lithium-ion battery cell, was $80 per kilowatt hour. But the cheapest battery cells, lithium-ion, are now $35 per kilowatt hour, in which case the sodium advantage sort of gets squeezed a bit. Now, sodium, one of the reasons why lithium ion was $80 kilowatt hour was lithium was 4 times more expensive than at the moment. So sodium is almost an insurance policy against us hitting limitations in lithium supply. If the lithium price ever did go up, and if you thought there were supply constraints that drove it up, then sodium is in the money. I think by the combination of lower price lithium and the potential for sodium, what we can predict is that battery cells will get cheaper and cheaper and cheaper. We then have to concentrate a lot on everything else apart from the cell, the whole of the balance of system costs. But basically, we have a set of technologies which are going to drive down the cost of the ion-based batteries. We also need to keep our eye on other technologies which are highly dependable, highly interesting at longer duration. For instance, there's a very interesting ones called iron-air batteries, which exploit, and it's almost, intriguing to understand. It exploits the process of rusting and derusting. Oxidation is it's like combustion. It produces energy, and reduction, derusting iron, turning iron ore back into iron, absorbs energy, and you can use that cycle. Now, the cycle has a large round trip inefficiency, but its capital cost is very low because it's very straightforward and you're using a very cheap material, which is why iron air might develop as an alternative even to hydrogen for some of these very long duration challenges where it doesn't matter that you're only cycling a few times a year because your capital cost is very low. So on cost, a set of interesting things happens, and then I think even more on performance. I said earlier, we're managing to increase the energy density of batteries, maybe doubling every 8 years. And as long as that continues, as somebody once said, compound interest is a wonderful thing. If you double every 8 years, you quadruple every 16 years, and then, beyond that, you go up 16 times every 32 years, et cetera, et cetera. And what that means is that whereas at the moment, I assume that batteries are only applicable at road transport and at the very short end of aviation, the sort of, 10-seater plane going 500 kilometers, but nothing like a jumbo jet getting across the Atlantic. I'm going to stick my neck out and make a bet for anybody who wants it, but I just warn you, the date at which we settle this bet is 2070, and I will be dead then, so you ain't going to get your money back. By 2070, we will have long-distance battery aviation, right? Because it will get there. If you look at the theoretical energy density, given the fundamental physics of what's called lithium air or lithium oxygen batteries, they have the energy density that can do that. So we can't rely on that. And the decarbonization of aviation up to 2050 has to be based on sustainable aviation fuel continuing to use a liquid hydrocarbon. But I think you have to assume that the energy performance, the energy density, and therefore our ability to support mobility, transportation, it will just be, for the next 50 years, on a relentless upward path, which eventually will achieve even long-distance aviation, even if we need other policies in the meantime. We can't rely on that. So those are different dimensions of where, the technology is going to take us in future.
Brilliant. Lord Turner, Absolute pleasure. I could talk with you for hours.
Well, thank you very much. It was
For
very
now, I think we
enjoyable.
have to wrap it up. Yeah, no, but I think it's a very good outlook there as well, and we keep our eye out on these other applications as well and opportunities. But yeah, no, for now, I really want to thank you for joining us for the Battery Insiders podcast. Lord Turner, this was an absolute pleasure of a conversation. I think great insights. On the market and getting understanding where we stand and where we can go. All the listeners today on the Battery Insiders podcast, if you enjoy these conversations, you want to listen more of them, please make sure to subscribe on Spotify, Apple Podcast, YouTube, or anywhere else where you listen to this podcast. We'd love to hear from you. Also, feel free to share your feedback with us. Always great to hear that. And yeah, for today, Lord Turner, thank you so much for joining. This was
Thank
Simon
you very
Engelke.
much indeed. Thank you.
Simon Engelke with Battery Associates, and talk to you soon. Thank you.
Bye bye.